Okay, welcome to my YouTube channel, Physics Matters. Today I would like to finish the part of kinematics by talking about projectile motion. Yeah, as you know, we talked already about the horizontal throw and the vertical throw, and now we generalize this further to be able to describe the motion of any object within the gravitational field of the Earth. So in order to do this, we want to write down the equations of motion, yeah, and it's very important that we use the plural form here because we will get two equations actually. And before we can write them down, let me draw again a coordinate system in 3 dimensions. So in principle, we only need 2 dimensions because everything will happen in one plane. In this case, the xz plane, but for completeness, I would like to draw all axes. And then we have an object here, which we throw under any angle, alpha, and then we can see it describes that kind of parabolic trajectory. So now, in order to describe this mathematically and to quantify that, we have to define a few parameters. So one, for example, is v0, the initial speed, as the absolute value, or the initial velocity in this case, when you take it as a vector. And then we also have an initial speed in x direction, vx0, and we have an initial speed in z direction, which we call z0. And if we add these vectors up, at the end we get our total velocity v0. And then we also have to define an angle alpha, which, for example, could be here. Yeah, this is the angle between v0 and vx0, which means the angle between the trajectory in the beginning and ground level. Yeah, so this is the angle under which we throw that object. And now we can also define a last parameter here, which would be the height of this object, and this is the distance between ground level and the object itself. So now we want to write down these equations of motion. So let me write down the most general form once more. R of t was given as 1/2 vector at square plus the velocity vector v0t plus any start vector r0. So now as initial position, so to say, yeah. And then we can separate these equations in the form that we use our superposition principle that we have stated before, and which allows us to separate the motion in x direction and z direction. Yeah? So we can now write down really 2 equations, one for x and one for z. So we start with the one for x, and this is given as, here we don't have any acceleration, yeah, in x direction. So this first term 1/2 at square vanishes, and we can directly write down the speed in x direction, which would be in this case x0 times t. And then we can always shift our coordinate system always in a way that we don't have any offset. So we can also ignore the last term r0. And now the second equation for the z component will look as follows. So we have an acceleration actually downwards, as we have stated many times before, and this is given as minus 1/2 gt square, the gravity, plus, and then we have to add again our initial speed, vz0, and times t, and then we have to also add an offset, which is in this case as r0, yeah, z0, and this would be in this case our height. Now what we can also do, we can use trigonometric functions in order to find a relation between vx0, vz0, and v0. So it turns out, when we take a look at this graph here, which we have drawn, that vx0 is the same as v0 cosine alpha, yeah, and then we have to multiply it with t. And in case of z0, this is the same as 1/2 gt square plus v0 times sine alpha times t plus h. And now we have 2 equations which are very important, and due to this reason I would like to highlight them as well. And these equations we will use now to describe or to calculate certain quantities related to the projectile motion. Another thing which we can also do, we can solve this first equation for t and then insert this into our t's that we have here in our second equation. Yeah? 1 time t and 1 time t squared. And this makes it possible then to write down only one single equation. Yeah, so I can write here inserting 1 into 2, and this results in z of x. Now our parameter is now not t anymore, it's now z. So we can write minus 1/2, and then we have to write here g divided by, and then we have to put in the denominator, we have to write v0 squared cosine squared. And then here at the end we also have to insert x squared. And then the same we have to do for the second term. Here v0 cancels out, and what remains is sine alpha over cosine alpha, and this gives tangent alpha, so we can directly write tangent alpha times x. And then our h also remains at the end. And then we can also highlight this equation here. So if we want to describe the motion of that object in our in space as a function of x, so the height of that object at any given position x, then we can use this formula here. We only need the initial speed v0, the angle alpha, and the height h in order to parameterize this. Okay. And this is, I think, very nice. And from this, we can now continue with the calculations of our quantities. So the first thing which I would like to calculate is the maximum height. I think this is an important quantity, which also makes it possible for us to learn a few things about projectile motions. So what we want to do, I will draw here another coordinate system with a general trajectory here. And then what we want to do, if this is x and this is z and this is x, so what we want to do, we want to calculate the height of that object at its maximum. So this we call z max. And the reason why we have this maximum is because when this object moves upwards, it is constantly accelerated downwards with g, with the gravity, until when it reached its maximum, the speed in z direction is completely compensated by the gravity, and then after that it starts to decline again. However, the speed in x direction does not change. We are only really talking about the speed in z direction. So what we can do, we can define our condition here, which means that z prime of t, or as we can also write dz over dt, the derivative of z with respect to the time has to be 0. When this condition is fulfilled, then our maximum is reached. We can also use the second equation that we have written down, z as a function of x, and then calculate the maximum by this. It would lead to the same result, but here I would like to do it in this way, because then we can also calculate the time in addition. So now let me briefly write down z of t once more, which was given as 1/2 g t square plus v0 times sine alpha times t plus h. And this we have to now, for this we have to calculate the derivative with respect to t. So here our 2 cancels out from t square, which means only minus gt remains. And then plus here our t vanishes and only the constants v0 sine alpha remains. And h also vanishes because of the derivative. And then what we can do in the next step, this has to be equal to 0. So what we can do in the next step, we can bring our v0 sine alpha to the other side. And this then results in gt minus gt is equal to minus v0 sine alpha. And then what we can also do in the next step is divide by minus g, because we want to get rid of the minus sign as well. So then we get here t equals v0 divided by g sine alpha. And this is our t max, the time when our object reaches its maximum. So this is again another important formula, I would say, so we can highlight that. And let me also briefly highlight one thing. So we have here our v0 over g. And if you remember correctly, this is the same formula that we also got for the time for reaching the maximum with respect to the vertical throw. And it also makes sense because the way how we derive this is exactly the same. We only have to take now here in addition this sine alpha into account, yeah, because this was the projection of the speed v0 onto the z-axis, so to say. So now we want to really calculate z max, the height. So what we have to do, we have to insert t max into z of t. And in order to do this, I would like to write down again z of t once more, which is minus 1/2 gt square plus v0 sine alpha times t plus h. And our t max we have calculated before. This was given as v0 divided by g sine alpha. Yeah, so when we do that, it turns out that we get here z of t max, which is then equal to minus 1/2. And then we have here our g, v0 squared divided by g square times sine squared alpha. Plus, and then we get v0 times sine alpha times v0 divided by g sine alpha plus h. Yeah, and then what we can see here already is that we can cancel out 1g in the first term, and we can also see that here we have v0 sine alpha times v0 sine alpha, which gives v0 squared sine alpha squared, the same what we also have in the first term. And then when we have minus 1/2 times a constant plus the constant itself, it's the same as if we write directly 1/2 times the constant. So we can write here 1/2 v squared sine squared alpha divided by g plus h. Yeah, and this is then in principle our formula, which we need to calculate z max. So then again, this is an important formula, and I would like to highlight this once more. And we will use this now to calculate an example. Yeah, so as always, I would like to draw this house here, which makes the calculations a little bit easier. And again, we have here a person standing on that with an object in his hand, but this time he throws this object under any angle alpha. And our trajectory would look like that. And then we can here define speed v0, and we can add any certain number here, let's suppose 10 meter per second. And then what we also need is our angle alpha. This is here, and this could be, for example, 30 degrees. And the last thing that we need is the height above ground level, which is given as 10 meter. Yeah, and then we can use our formula for z max in order to calculate the maximum. And if we want to do that, we can write down here z max, and then once more the formula 1/2 v0 squared sine squared alpha divided by g plus h. And now we only have to insert our values actually, so 1/2, and then we have here 10 meter per second squared sine squared of 30 degrees divided by 10 meter per square second. And the reason why I use these values is because now we can see many things cancel out. So of course one of these 10 meter per second cancels out with 110 here downwards in the denominator. And what we can also say is that sine of 30 degrees is easy to calculate. This is simply 0.5. So our sine squared of 30 degrees is 0.25. So now we can calculate 1/2 times 10, which is 5. And then 5 times 0.25, which is given as 1.25. And then of course we also have to add our h here, which was 10 meter. Yeah. So at the end we get a value of 11.25 meter. Yeah. And this is the maximum height that can be reached. It starts from a height of 10 meter. So actually what it means is that our object travels 1 meter 25 upwards, and then it falls down again after that. Now we want to calculate the maximum distance that we can throw this object. So in order to do this, we could either use again z of x, but in this case I would like to do it by first calculating the time again. So we can also calculate the time of flight of our object. And in order to do this, we use again our function z of t, sorry, which has to be then equal to 0. Yeah, when z of t is equal to 0, it means ground level is reached. And then in this case, we can insert our z of t. So I will write it down again, minus 1/2 gt square plus v0 sine alpha times t plus h. And then we can directly multiply it with -2 and also divide it by g. Yeah, so this also has to be equal to 0. So what comes out at the end is that we have here our t square minus 2 times v0 divided by g sine alpha times t minus 2h divided by g, and this also has to be equal to 0. And the reason why we have to write it in this form is because we have now a quadratic term t square and also a linear term with t, so we cannot solve this equation directly for t. We have to use PQ formula for this. And for this purpose we have to now first define our value p and our value q, and then we use PQ formula to solve this. So at the end we get two solutions, t12, and this is p half, which would be v0 sine alpha divided by g, and then plus minus square root p half squared, so it would be v0 squared sine squared alpha divided by g square, and then minus q, so we have to write here 2h divided by g. Yeah, and this is in principle our solution. We can rearrange this a little bit further. So first of all, I would only concentrate here on this positive sign. The negative one we can reject, and then we can also take out 1g from this square root, and at the end write everything on a common denominator. Yeah, so what we can write now here is the same as v0 sine alpha plus, and then square root v0 squared sine squared alpha plus 2gh divided by g. Yeah, this makes it a little bit easier later for calculations. And yeah, this is actually our TD, let's call it TD, the time which our object travels until it reaches its final destination. So again, this is an important formula, and due to this reason I like to highlight it once more. And now again, as usual, we calculate a simple example for this. So again, we use our same parameters. V0 is 10 meter per second. The height was given as 10 meter, and our angle alpha is 30 degrees. The reason why I choose these values is because I want to show you now that although the equation looks very complicated, yeah, we can solve it without any calculator. So then we can calculate our TD, and this is given as V0 sine alpha plus square root V0 squared sine squared alpha plus 2h0, yeah, divided by g. This was the formula that we derived from before. And now we can say, we can insert our values. V0 is 10 meter per second, sine of 30 degrees, plus, and then square root, then we have here again 10 meter per second, squared, sine squared of 30 degrees, plus 2 times 10 meter per square second times 10 meter for the height. and then all this has to be divided by 10 meter per square second. Okay, so now what we can already see here in this case is that we have here 10 meter times sine of 30 degree, and I said before this is 0.5. So here we have actually 5 meter per second. And here in our square root, we have 100 times 0.25 because sine squared. And this would give a value of 25. And here we have 2 times 10 times 10, which would give a value of 200, in this case meter squared over second squared, and here also meter squared over second squared. And what we have then is 225. The square root of 225 is 15 meter per second, plus 5 gives 20 divided by 10. So what we can write here is 5 meter per second plus 15 meter per second divided by 10 meter per second. So at the end this results in 20 meter per second divided by 10 meter per second, and this gives as a result 2 seconds. Yeah, this is our time that the object travels until it reaches ground level again. So now the only last thing which we have to do in order to calculate the maximum distance is that we have to insert td into our function x of t. Yeah, so xd would be then given as x of td, and if we write this down, x of t was given as v0 times cosine alpha times, and then we have to insert our td, which is v0 sine alpha plus v0 squared sine alpha squared plus 2gh, and this everything divided by g. Yeah, we can make a few changes here in this formula, but nevertheless it will not become much easier than that. So I think this is the way how we have to do it, and I think we can actually also highlight this as an important formula. So now we can calculate also an example. Again, we will use our initial speed of 10 meter per second. We will use our height of 10 meter and our angle alpha of 30 degree. So now we have already calculated td before, and this was given as 2 seconds. So what I will do, I will not calculate this whole equation again, but I will just simply write down here xd, which is x of 2 seconds. So I will write here v0 cosine alpha times 2 seconds, which is 10 meter per second times cosine of 30 degree times 2 seconds. This at the end results in approximately 17 meter. Yeah, this is the distance that our object travels before it hits again ground. Yeah, I hope this video was very helpful to understand projectile motion. This is everything what I will want to cover in this video. I hope that you enjoyed it, you learned something new, and thank you very much for your attention. Thank you very much for watching this video. If you like the content and want to see more of it, please like and subscribe. And in addition, any kind of support is always appreciated.